problem solving and mechanics today. So let's begin. So first of all, I'll be putting up the solution of the question in kinematics that I had given you last time, the approach velocity application question in just a bit of time. But before that, today we will start with discussion of constraint relations in Newton's laws of motion, friction, circular motion, etc. In all the chapters ahead, including applications in center of mass, work, energy, etc. How we make use of constraint relations using the virtual power concept. So let's begin with that. So virtual power theorem. And applications for constraint relations. So as you know, the statement of the virtual power theorem is that the net power developed by internal forces like tension, normal contact force, etc. in a system must be zero. Okay. And when we talk about power, we are talking about instantaneous power. Okay. So as a very simple example of that, let us look at a problem involving system of pulleys. Suppose we have a situation like this. So all three pulleys are massless. And we want to find the constraint relation between, let's say, the upward motion of A's velocity and the downward motion of B's velocity. So P1, P2, and P3 are massless, smooth pulleys. And all threads are also massless and inextensible. So you want to find the ratio of VAs to VB. Yes, very good, Nishit. That's correct. Okay. So this is a typical system where instead of applying the conservation of thread length or the concept of approach and separation velocity, which would basically involve conservation of thread length, we preferably apply the concept of virtual power. So let's understand the application of that. Yes, Aditya, that's correct. So what we'll understand here is that if the tension in this string is T1, okay, and the tension in this other string is T2, So first of all, by looking at the free body diagram of the massless pulley P3, we can see that the relation between T1 and T2 is that T2 is twice of T1. So T2 becomes twice of T1. And like that, suppose the tension in this other pulley, in this other thread is T3. Okay, then further we have similarly T3 becomes twice of T2 or 4 times T1. Okay. Now we can see that as far as the block A is concerned, there is a net tension of T3 plus T2 plus T1. So that will be 7 T1 acting on it. So if it has an upward velocity of VA, okay, and similarly on B, there's a net tension of just T1, but it has a downward velocity of VB. Okay, now if you look at the other pulleys, so power developed by tension will be equal to plus 7 T1 VA minus T1 VB. This should be 0. Now, why the powers developed by tension on these pulleys have not come into place? Because the net tension on each of the pulleys is 0. The net tension on each of P2 and P3 is equal to 0. So even though they are moving, okay, so even though they are moving, the power developed by tension is 0. So this tells us that the ratio of VA is to VB is equal to 1 is to 7. VB is 7 times VA. Okay, so this is a very standard application of this virtual power concept. Okay, now let's look at a somewhat more interesting application of virtual power concept. So this is a fixed smooth pole. I have a ring of mass m1. So this is a fixed ceiling. And we have here a block of mass m2. Now we will convert this into this will become a problem of work energy. So this angle is theta. Okay. And also this length is given to us. So given that m2 is equal to, let us say, 4 times m1 and L is equal to 24 meters, the system is released from rest at theta is equal to 37 degrees. Okay. Find the speeds of the ring V1 and block V2 at the instant when theta is equal to 53 degrees. So take G as 10 meters per second square. Okay. So first of all, what I want you to do is find V1 is to V2 ratio when theta is equal to 53 degrees at that instant. And then find the value of V1 in meters per second, V2 in meters per second. Yes, very good, Ganesh, that's correct. So here we could also do it by the approach velocity concept that we've discussed in last lecture. But I want us to solve this by the virtual power method to get additional practice on the concept of virtual power. Nishit, you've taken theta as 37 or 53? Yes, Bhumik, your answer is correct. Yeah, yeah. Just check the value, Nishit. Okay, so yes, Aditya, that's correct. Okay. So once again, at some intermediate instant, when this angle theta is got some general value, at that moment, if this ring is going vertically upwards at some speed v1 and the block is coming down vertically at some speed v2, instantaneous speeds or velocities v1 and v2, and of course the tension acting here is t and the tension acting here is 2t, whereas the tension acts at these points which are stationary points, so you don't have to consider power. So net power developed by tension should be zero. So here on the ring, the power developed by tension will be Tv1 cos theta. Okay, and on M2 it will be minus 2T V2. So this should be 0. This is on the ring, this is on the block. And nowhere else you can see tension is delivering any power. So we get this relation that V1 is to V2 is 2 is to cos theta or 2 sec theta. Okay. So at theta equal to 53 degrees, this V1 is to V2 will become 10 is to 3. Correct. So this should be the answer to the first part. Okay. Now second part, you have to work out a little bit geometrically. Okay. So So second part, let's say this is when theta is 53 degrees and this has got some speed v1. This has got some speed v2. But earlier when theta was 37, let us say the system was this was at rest. This was at rest, but this theta was 37 degrees. Okay. So we have to understand how much vertical displacement this one has had and how much vertically upward displacement this one has had. So we can see S1 will be equal to L into, so this vertical side, so it will be L sorry cot theta. So it will be cot 37 minus cot 53. So it will be, you can L as 24 meters. So it will be 24 into 4 by 3 minus 3 by 4. So S1 will be 4 meters, sorry, 14 meters. Okay, Ganesh, just check out the steps. Okay. Now S2 will be such that 2 times S2 is equal to the change in the hypotenuse, the thread length. So that is, so L upon hypotenuse is sine theta. This is cosec 37 minus S2 would be 24 by 2 into 5 by 3 minus 5 by 4. So 60 by 3, that is 20 minus 60 by 4, that is 15. So it's 5 meters. So Ganesh, have you got the same values of the displacements S1 and S2? Just check these out. Okay, very good. So now you apply work energy theorem. So conservation of mechanical energy. So should be the relation here. So we have taken the ratio of the masses. M2 is being taken 4 times M1. So half M1 V1 square we can say, plus half M2, which we can write as 4 M1, because M2 was 4 times M1, and V1 by V2 is 10 by 3. So V2 we can write as 3 by 10 V1. Is equal to 4 M1 G into S2 which is 5 minus m1g into s1, which is 4. So I believe this is the answer we should get. Ganesh, I'm getting a slightly different value. Just check the steps. Yeah. So up to S1 and S2, you got the same, no? And it should be a matter of okay. Okay, okay, then it's fine. And V2 is just 0.3 times this, so we just multiply this with 0.3. Okay, so this is another example of the application of this type of constraint relation. Okay, so you can check out the full solution later. Okay, so moving on to more examples of application of virtual power constraint relation. So next example, we have this situation. We have say a triangular wedge like this. Kept on a smooth horizontal surface. And now we also have this kind of an object. just fits over here. This is a smooth surface. This is a smooth surface. And this angle is theta. So this wedge is of mass m1 and this rod, but with the side of the rod cut like this to fit this angle theta exactly. So this thing is of mass m2. So given that theta is equal to 30 degrees and m1 is equal to 2 times m2, we have to find their accelerations when released from rest. Yes, very good, Ganesh. That constraint relation is correct. So here also, I'll make use of the virtual power method of calculating the constraint relation. So see, I know that the wedge is constrained to move in the horizontal direction. So let's say at some instant, it has a horizontal velocity of v1. Okay. And the normal reaction applied by the block or by the rod on the wedge, that is along this sort of direction, the normal direction. So now the angle made by the incline with the horizontal is theta. So this angle will become 90 minus theta. As you know, this angle is theta. Okay. So the power by normal reaction on the wedge, that will be plus nv1 cos theta. Okay, now similarly, if we look at the situation of this rod, now this one is coming down vertically with an instantaneous velocity, let's say v2. Okay. Whereas the normal contact force that this applies on it is now at an obtuse angle to it. You can see it's acting like this. Okay. So you can see that this angle is 180 minus theta. Oh, sorry, this is cos 90 minus theta, my mistake. So this will become sine theta. That's correct. Okay, so the power delivered by this normal reaction on M2, this will be NV2 cos 180 minus theta. So it will be minus NV2 cos theta. So this is the power delivered on M2, on M2 rather. Okay. So now this action reaction pair on this system, the net power delivered by this normal reaction action reaction pair, this should be 0. So okay. Okay. So now we can differentiate this and say that A1 is to A2 is root 3 is to 1. So this becomes our first important equation. Okay, because theta was 30 degrees and M1 was 2 M2. So we'll make use of these now. Now let's come down to free body diagram. So on this wedge we have normal reaction applied by this. We have its own weight. We have normal reaction applied by the ground. And this is having a horizontal acceleration. So A1. Okay. So this is pretty simple. As you can see, if this angle is theta, then this angle is theta. So we have n sine theta is equal to m1 a1. That's our second equation. Yes, Nishit, it's correct. Your answer is correct. Okay. And then on the rod kind of thing, we will have these kind of forces. So one normal reaction here. its own weight, some kind of normal reaction with the wall. M2G, some normal reaction N2, this normal reaction N. Okay. And so again we can see that this angle is theta, meaning that this angle is theta. Okay. So for this we have the equation now that weight minus N cos theta is equal to M2A. So that's our third equation. Yes. N2 will balance N sin theta, but that's not really necessary. So now these three equations, we'll just make use of them. This, this, and this. Okay. So let A2 is equal to A. So A1 becomes root 3A. M2 is equal to M. So M1 becomes 2 times M. Yeah. And theta is equal to 30 degrees. So this becomes N by 2 is equal to 2M into root 3A. And this becomes mg minus root 3 by 2n is equal to mg. This equation becomes this equation becomes this. So substitute n from here into this. Yeah, so I'm getting some different values. No, just check the equations once all of you are not getting the same answers. Bhumik, you are getting the same, but Nishit and Ganesh, your answers are not matching with this one. Okay, let's do this parametrically if you want. Okay. So parametrically, if we look at it, then we have okay, we have this. Okay. So A2 is equal to A1 tan theta. This equation n sin theta M1 A1 and where is the last equation now? Yeah, M2G minus n cos theta was equal to m2 a2. Okay. So we can substitute this here and we can substitute this here. So we'll get this is equal to m2 into a2, which is a1 tan theta. We get okay. So now let's just check this parametrically. So theta is 30 degrees and m2 is twice of m1. No, m1 is twice of m2. Yeah, so I'm getting that. So this is all just about practice. One has to be a2 is not even tan theta. Let's check. You're getting that now. That's how I got this now. Yeah. Anyhow, so you have to just be extra patient and careful while doing this type of question. So let's go over the solution once more. So first thing, virtual power method to get the relation between the instantaneous velocities, and you can differentiate that to get the instantaneous acceleration relation. Okay. That's how we got this. You can also get this geometrically. You can understand it this way, that if this was the situation initially, now after some time, this has gone here. Yeah. And this is moved here. Okay. So this and this. This is S1. This is S2. Okay. And this angle is theta. So you can see that S2 by S1 is equal to tan theta. So S2 is equal to S1 tan theta. So V2 is equal to V1 tan theta. Okay. So anyway, the whole point here was to practice the constraint relation by virtual power methods. So I've done that. Okay. Anyhow, so the first thing is that we got the ratio of A1 and A2. So I took A2 as A, so A1 became root 3A. Okay, so from this constraint relation, I've got this. Okay. Then free body diagram equation of this. Okay, so this has reduced to put theta equal to 30 degrees. So this reduces to this. Also the fact that M1 is 2 times M and theta is 30 degrees. The second equation becomes this. And the rest is just substitution. So again, the thing is at advanced level, you have to be quick in doing these type of calculations. Okay, now let's move on to something a little bit more involved with application of constraint relation. So I'm going to do a bit of a jump in terms of chapters, and we're going to discuss something that involves a bit of rolling. Okay, but all of you are familiar with rolling, so it should not be a problem. At least the basic concept of rolling is clear to all of you, so it should not be a problem. Okay. So we have this spool kind of object. Which is rolling on the ground. So three-dimensionally, this object looks like this. Now, there is a thread wound on the spool, just coming out like this. So it's attached. This kind of situation. And now the other end of the thread is attached to the block. It's like this. And this here is a rough surface. Okay, so given this spool has the radius of outer V inner cylinder R. So this is the inner cylinder, and these are the has radius equal to R again. So at an instant when the spool A is rolling on the rough surface with speed equal to 1.8 meters per second. If R is equal to 5 centimeters. Find omega A, omega of the pulley, and VB, and the thread is at, so this angle at which the thread is there with respect to the horizontal, this angle theta is 37 degrees. Okay. So this is all the information that is given. No, Ganesh, you have to be a little bit careful. There's an inner radius and outer radius. So first tell me how much will be omega A and omega B, or and omega of the pulley. Okay. So the thread does not slip at either of the pulley surfaces. Okay, that we have to consider. Yes, that's correct. So then you have to think what is the omega of that pulley. Or you can directly think VB and that speed also, but it will be, I think you just made an algebraic plus minus mistake. Otherwise your answer would have been correct. Okay, so this question is a little bit more complex. Let's understand each element at a time. So the easiest part is of course the rolling motion of the spool. So that's pretty easy to figure out. So if the center of mass of the spool has a speed VA, and about the center of mass there's an angular speed omega A. Then because this point of contact has to be at rest. So this has to be at 0. That means, now remember this radius is 2r. So VA is equal to 2 times r omega A. Okay, so that's the first thing. Okay. Now let's talk about the thread which is coming out from somewhere here, let's say. So this angle is theta. So you can see that if I just call this point as, let's say, Q or something, velocity of the point Q with respect to the spool, that will be equal to r omega. So that will be VA by 2. Okay. So velocity of the point Q on the thread will be the velocity of Q with respect to the spool plus the velocity of the spool. Okay. So if this part of the thread is having tension T1, okay, so at this point where Q is present, you can see that the net velocity of Q is the vector sum of VA like this and VA by 2. And the tension T1 is acting in this direction. So this relation I've tried to show you. This is the velocity of the spool. and this is the velocity of q with respect to the spool. This relation. Okay, so power delivered by this tension T1 on the spool is this T1's dot product with velocity of that point q. Just take this point q as this one. So that you will see here from this diagram, this power becomes T1 into R omega plus VA cos theta. So it becomes plus T1 into VA by 2 plus VA cos 37. Okay, so this is the power delivered by the tension T1 on the spool. Whereas the second thing it's delivering power on T1, which is the pulley, that's very simple. So on the pulley, it's a very simple situation. This is rotating at some omega. Okay. And the tension T1 is just acting at this point. So this point where it's acting, it's having a velocity of r omega p. So now this thing, power delivered by tension T1 on the pulley, that is just minus T1 into r omega p. So the net tension should be zero. I mean, net power delivered by tension should be zero. Okay, so from these two now we have that okay, and you will see velocity of the block is this much only. So velocity of the block will come out to be VA upon 2.6. We have taken but that will come in the second one, which I'm not writing separately. But now if we take into consideration, Bhomik, the second string part of the thread is actually the same thread, but the second part of it. So if we take that into account, the block attached. Now, because it's a rough surface, no, so tension will be different. Okay. So this is moving down at the velocity v2 or vb, whatever. So from that only we'll get this other relation, this one. Understood, Bhumi? But that's a simple one, so I'm not gone exclusively into that. Okay. We can also understand this by a superposition kind of method. I will explain that in a minute, but just first make sure you got this. Okay, so this is a bit of a complex type of question. Now let's do this. Suppose we are not using virtual power method, then we would have to use the conservation of thread length method. Even that is feasible. That's not too difficult here. Let's understand how we would have done that. Okay. So obviously the first part V is equal to 2R omega that you have got. That is nothing to do with thread length. That is to do with the no slipping condition. Okay. Now next what you do here is you apply superposition method for understanding the relation between this omega and this. Okay. Now suppose this was only spinning. If this was only spinning at omega A, then what would happen? This thread would be going from here at the rate of r omega A. So it should be winding here at the rate of r omega p. The r's are the same. Okay. And similarly, now imagine that this is not spinning. This is only translating. So suppose this was only translating. Okay. At a rate VA like this. So you can see that this angle is theta. So this has an approach velocity in this direction of how much? VA cos theta. So this would again wind in the wire at the rate of VA cos theta. So that is how this net is becoming like this. So that's how we were getting omega p as 1 by r VA cos 37 plus r omega a. And remember 2r omega a was equal to VA. So R omega A was BA by 2. So that's how we got this. Got this equation. Okay. And then whatever rate this is winding at, it's releasing string at that same rate over here. So that becomes the rate at which. Okay. So that's how we get this relation. Just one thing here, this should be in the numerator, not in the denominator. Small correction. Okay, so I hope this constraint relation concept is clear to all of you. Okay, next I want to discuss some types of problems involving pseudo force and application of limiting friction, both in the same place. So this is a smooth surface. This is a 37-degree wedge of mass capital M. And this surface is having a coefficient of friction of 0.25. And there's a block of mass small m placed over here. Now we are applying a horizontal force like this on the system. So given that small m is 1 kilogram, capital M is 4 kg. Coefficient of friction I've already given you 0.25 and g is 10 meters per second square. Find the range of values of f such that there is no slipping between the block and wedge. Okay, just work this out quickly. this force F that we are applying, it's a horizontal external force. Okay, so I'm verifying the answers. So what we'll do here is we'll make the free body diagram of the block in the wedges frame. So we are in the non-inertial frame moving with a horizontal acceleration A like this. So the forces acting on the block, people like this. So coming back to this, there is pseudo force. Okay, there is weight and there's normal reaction. Now we assume that if MA cos theta is less than MG sin theta, So it has a tendency to slip down. Down the incline. So friction acts up the incline. Okay. So in this case, we should take the direction of static friction like this. Okay. So the condition for the equilibrium in this frame is as follows: that normal reaction is the sum of mg cos theta plus ma sin theta, and static friction plus ma cos theta balances mg sin theta. Okay. So from this we will get that static friction so this static friction should be less than equal to mu n. So mg sin theta minus ma cos theta should be less than equal to mu into n, which from above is mg cos theta plus ma sin theta. So from this you can see that we'll get a condition on A like this, that A into cos theta plus mu sin theta. I've taken this that side, so this will become greater than equal to g into sin theta minus mu cos theta. So I'll get a condition like this, that A should be greater than equal to g into tan theta minus mu upon 1 plus mu tan theta. So this is telling me that A's minimum value is equal to g into tan theta minus mu upon 1 plus mu tan theta. So that will be over here 10 into 0.75, because we've taken theta as 37, correct? And mu is 0.25, okay, upon 1 plus, so that will become 1 by 4 into 3 by 4, so 3 by 16. 10 into half divided by 19 by 16. So 80 by 19, or approximately 4.21 meters per second square. This is the minimum acceleration that I can give the system. Okay. Now I'm going to apply an important shortcut here. Okay. So when we look at this free body diagram, now in contrast to this, if ma cos theta is greater than mg sin theta, then contrastingly what is happening? The tendency is to slip up the incline. So accordingly friction acts down the incline. So the difference is just the direction of friction. The rest of the things remain the same. So here when we apply the condition, we will see that just wherever friction is there, we'll just replace it with a minus sign. So this equation becomes this. Okay. So wherever there's a mu in the final answer, we replace it with a minus sign. So this will give us this kind of inequality now. This inequality will become like this. This will become A is less than equal to G into mu into tan theta plus mu upon 1 minus mu tan theta. So from here, our A max will come out to be okay. So that will come out to be 10. So correspondingly, the maximum acceleration will be about 12.31 meters per second. So this is a little trick that I wanted to discuss through this question. That whenever we are solving a limiting friction condition like this, where we have to do the maxima minima condition, okay, that in the maximum external force case, the friction is preventing slipping from occurring up the incline. So friction is acting down the incline. Whereas in the minimum condition, friction is preventing from slipping happening down the inclined plane. So friction is acting up the inclined plane. So we can actually just do a comparative study of the two equations. Equation 1 here will be the same. But in equation 2, friction is replaced with a minus sign. So when we solve later, replace mu with minus mu, because only the direction of friction has got reversed. Rest the limiting condition and all is the same. Okay. And now to find the external force F, make a combined free body diagram of the wedge plus the block, because they are moving together. So F will just be capital M plus small m into A. So this range of A will give you the range of F correspondingly. So it will be between 5 times A minimum to 5 times A maximum. That is the range of force. So this kind of competence in doing these calculations fast you should have the JEE level. Okay, so next step, what we can do is we can make a combined free body diagram of the wedge plus the block as one object, because there's no slipping happening between them. So this is going at an acceleration A. There is combined weight, some normal reaction from the ground, let's say N prime, and only one horizontal force F. So F is equal to M plus M. So therefore this force must be less than equal to this maximum and greater than equal to this minimum. Okay, so we just substitute the values of A max and A minimum. So I will show you a question in JEE which was similar to this in application of the limiting friction condition in just a moment. Okay. I'm sure at some point of time you have done this question also, the one I've just discussed. This type of question you must have done. Or there's a easier version of this question where there's no friction involved. So you have to just find the amount of force required to keep the block stationary. So in that there's no friction. So just your MA cos theta is to be balanced by mg sin theta. So you get one possible value of acceleration, one unique possible value of acceleration, which is g tan theta. So instead of a range of force, there's a particular value of force that prevents slipping. But here, because there is friction involved, there's obviously uh, there is a range of forces possible. Okay. So, for example, an easier level version of this question is something like this. You just have a rough inclined plane. Just have a rough inclined plane like this on which you've kept a block of mass m. This has a coefficient of friction mu. Mu is less than tan theta. Now we have to just find the range of force that we can apply so that the block remains stationary. Okay, so this you should be able to answer pretty fast now. So you find the range of F such that the block M is stationary or remains stationary. Remains stationary in equilibrium. Okay. So you can see that F's maximum value will be how much? Okay, let's take numerical values. This will help. So take theta as 37 degrees again. Take M as 5 kg, G as 10, and take mu as 0.5. So I want you to work out the answers pretty fast. What is this maximum? What is this minimum? Yes, very good. That's correct, Nishi. So the minimum condition will be when maximum friction is acting up the inclined plane. So this will correspond to the minimum. And correspondingly, the maximum will be just reverse this. So it will become replace mu with minus mu. Okay. So F will be anything between 50 and 10 newtons. So you can see mu is less than tan theta, na Aditya. So we need to apply some force to keep it in equilibrium. Otherwise, it will slide. There isn't sufficient friction. So there are many versions of this type of question. So just make sure that you are aware of this. Okay. Now we'll do one example of a JEE advanced question based on this. So A and B are of equal mass 1 kg each, and both these surfaces are rough. Okay. And the wedge C has a mass of 8 kg, and this is a smooth surface. Now same kind of problem, we are applying a horizontal external force. So try and get this correct numerically. So find the range of F, which is a horizontal external force. To keep A and B in equilibrium with respect to C. Okay, so let's verify this. Now again, I'm going to use a direct free body diagram here. So let's say we are in this frame which is accelerating like this at T. We are in this non-inertial frame. So in this frame, we will see what all forces acting on these blocks. We'll see pseudo force, pseudo force, weights, obviously there is tension in the thread, and there's going to be normal reaction on each of the blocks. Okay, now we come to the condition of friction. So if E is minimum, okay, the tendency to slip is such that mg dominates. But which one's mg? B's were pseudo force on E. Because you can understand mg acting on B is trying to make the system slip like this, whereas pseudo force on this is trying to make it slip in the opposite direction. So if this dominates, then the friction should act like this. Should act like this. So the condition we have is that mg should be balanced by ma plus fa plus fp. So for A equal to A minimum, mg should be balanced by ma plus mu mg plus mu mg. So from this we will see that we will get A minimum as g into 1 minus mu upon 1 plus mu. Okay. Now correspondingly we can see if the opposite were true, for A being large, okay, ma on the block A dominates over mg on the block B. So direction of frictions get reversed. Okay. So from that we'll get the maximum acceleration as g into 1 plus mu upon 1 minus mu. So this trick we can use over here. So we will get from this and this, we'll get E is less than equal to yeah. So now you make the combined FBD. So you can see that F will be less than equal to 2m plus capital M, and yeah. So these are the values I'm getting. You can just go through this once and check the equations also yourself, what you have done. Okay. Yes, I will discuss that question next. Okay, so before we come to a close for today's class, next lecture I'll be discussing some circular motion concepts going into rotation from there, and separately also applications of work by energy along with center of mass. Okay. So now we'll start combining concepts in mechanics together. So we'll do those type of situations where there's application of conservation of energy as well as conservation of momentum, or application of work by energy or work energy theorem along with some center of mass concepts, etc. Okay. And few things particularly in circular motion we'll discuss, and certain variations of circular motion involving the application of the general concept of instantaneous radius of curvature, etc. So those are the things coming up in the next lecture. Now I will discuss the kinematics problem that I had given last time. So hope you got a chance to go through that question fully. So in this question, what was happening is that we had one particle go off with a velocity in this direction, and the other one chasing it with a velocity in this direction. Where this angle was some alpha or whatever. So this was the situation at t equal to 0. So after some time, let's say what has happened is that at t equal to some instantaneous time t, A has reached here and B is here. So at this particular moment now, the velocity vectors are like this. So as you can see, A's velocity vector is continuously changing direction, whereas B's velocity vector remains fixed in direction. In fact, A has a fixed velocity itself. Okay. So if we take this angle as an instantaneous theta, so we can see that V1 minus V2 cos theta is the instantaneous approach velocity of A towards B. Okay. This is the instantaneous approach velocity of A towards B. So the distance between A and B is S at some instant. And initially that distance was whatever the D was. Okay. So that is minus ds by dt. So eventually after some time, if they collide somewhere here, okay. So this is gone on this kind of path and collided like this. Oh, just a minute, I will having some connectivity issues, I think, so I'll just share the screen again. Yeah, so have you got the screen refreshed now? The screen is not refreshed. Okay, okay. Just a minute, I'll have to. Let me see if I can. Yeah, so people, has the screen refreshed for you? Are you getting the whiteboard screen? Still loading. Okay. Okay, so there's some problem with the net connection at my end. So we will pick this question up in the next lecture. Okay, I will send you the solution as part of today's PDF, but I will discuss the question steps in the next lecture. Unfortunately, the internet connection is not working properly. I mean, the data rate is very slow at my end. Okay, so we'll have to call it a day. That's it for today, people. So wish you all the best and continue working on the problems and sharing your doubts with me on WhatsApp. I will discuss as much as possible.